Welcome to the AP Physics video lecture. This is covering the unit of torque and rotational motion. The section here is going to be on rotational kinematics. We're going to first talk about what the radian unit is. If you take a look at the arc here, if you want to go and walk around the distance around this circle, it's going to be defined by the arc length of L, is how much you're going to be traveling right here. That's going to define how far you travel, and that is going to determine on two values, that radius r and the angle theta. The length or the arc length can be defined by multiplying the radius with the angle. The radius with the angle multiplied together will get you the arc length. Another version of this equation can be defined by this. The arc length, the angle, is equal to L divided by the R. That's just when you divide the R to both sides. We know that for a full circle, the angle is going to be considered to be 2 pi. That unit is radians. In degrees, we can see that 360 degrees is the same thing as 2 pi radian, which is equivalent to us in any problem saying 1 complete revolution. An easy way to memorize this is that in the circle world, you use the units of radians or rad. In the line world, we use the word meter. So when you see meter per second, you're going to see radians per second. A typical problem that you might see is that it asks how many radians did a bike rotate if it had 5 revolutions. So 1 revolution is 2 pi. So 5 revolutions would be 5 times 2 pi. And if you simplify that, you get around 31.41 radians. What you should consider here to help you along with this idea of the angle is that it doesn't matter how much you go around the circle, it's always going to be 2 pi. Next, we're going to talk about the angular velocity. We know that in our line world, where we're going to call it translational, and in the circle world, we call that rotation or circular. We know in the line world, displacement is going to be the change of x is equal to the final location minus the initial location. In the circular world, we use something called angular displacement, which is called theta. So delta theta is equal to theta final minus theta initial. If you want to take a look at this circle, you can say that right here, this would be its theta naught, and then it's going to go up this arc, then it's going to reach a theta final. All right? The displacement on this arc would be delta theta. That is how much it traveled along that arc. If we solve for angular velocity, we know that velocity is the displacement over time. We can take the slope of the displacement over time, and we're going to get that to be the velocity, and the units for that is meters per second. Likewise, in the angular world, it now becomes something called angular velocity. We call that omega. The way I think about it is that, do you see how velocity looks like a V? You just add an extra V here, and it just becomes angular velocity. Okay. Likewise, it's going to be change in theta divided by change in time. And that unit is going to be rads per second, which is equivalent to meters per second. What I want you to see is that all points in a rigid object will rotate with the same angular velocity, since every point in that object moves through the same angles at the same time interval. This is like Kepler's second law. So if you put an object here, or an object in the corner, or the object right here in the middle, all of them will experience the same angular velocity. So this is A, this is B, and this is C. So the angular velocity of A, the angular velocity of B, and the angular velocity of C, they're all the same. The reason why they're all the same is because they are changing, because they have the same change in angular displacement. Okay. That's why. This is very important for you to understand this. Next, every single point of a rotating object has at any moment a linear velocity v. We also call that the tangential velocity. This means at this point right here, it's going to have a tangential velocity v. That tangential velocity is going to be defined by r omega. This is the velocity which is equal to the radius multiplied by the angular velocity. This is what's going to change. So notice here that since the omega, which is the angular velocity, is the same in every single rotating object, the linear velocity is greater as you move away from the center. So the linear velocity changes as a function of the radius. So let's say here would be VA, then here would be VB, then at the end it's going to be VC. We would say that VC is going to be greater than VB, which is going to be greater than VA. Why? Because V, linear velocity, is equal to radius times omega. The radiuses here are different. That's the reason why. Radius of C is greater than radius of B, which is greater than radius of A. So the linear velocity is changing as a function of radius. The angular velocity doesn't change. So let me repeat. The linear velocity changes as a function of radius. The angular velocity does not change as a function of radius. We're going to look at a problem here for the angular velocity problem. A vinyl record, like our last problem, is recorded on a graph. The needle traces out a circular path as the record spins with a radius of 2 meters. You're going to determine the angular displacement of the needle for the first 2 seconds. The approach for this problem is that this is the angular speed. So if you want angular displacement, you would have to take the area under the curve. So the area under the angular speed versus time graph will give you the angular displacement, like how the area of velocity versus time graph will give you the total distance traveled. Here it's a triangle. From, if you take a look, this is the area of a triangle. So you can use the area formula of a triangle. So the angular displacement is going to be 1/2 base times height. The base here is 2. And the height here is going to be 20. Multiply that together, you get 20 rads. So in that 2 seconds, the object is going to travel 20 rads. Next question. What is the translational speed of the record at 2 seconds? Well, we know the formula for velocity is going to be radians, the radius times the angular velocity. And we want to know what the speed is at 2 seconds. So it's right here. So at 2 seconds, the speed here is going to be at 20. So this is, let me clean everything else. So, right? That point is going to be 2 seconds is going to be 20 angular speed. So we multiply 2 times 20. That's going to get you 40. This is going to the speed of the record at 2 seconds. Okay, this is the translational speed. All right. So this is V of t. You might see this as V of t. Okay. Next, graph the angular displacement versus time. And so it's exactly like this. Okay. We know that to get the angular displacement, okay, the slope of the angular position versus time graph represents the angular velocity of a point of an object that rotates. As time increases, the slope of the graph will increase because the angular speed of the system will increase. All right, so let's take a look. So from 0.0 to 0.5, if we take that area, this is going to be 1.25. So it's going to be like right here. Okay, this is going to be 1.25. Then next, let's find this area. Okay, that's going to be for 1 second. And next, for the 1 second, we find this area. That's going to be equivalent to around 5. So this is going to be right here, around 5. Then for 1.5, we find that area. That was around right here, 11.25. Then last one, we did that. That was equivalent to 20 rads. So that is right here. Okay. And we saw that this is going to go up exponentially. That would make sense because remember, to go from here to here, you have to take the slope, right? This is an x squared term with this, which is a quadratic. And once you go up, this becomes an x1 term, which is going to be linear. All right. Okay. So the next part of this is going to be in the second video. All right.